Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed that if a single rectangular pulse of acceleration or acceleration pulse of amplitude A is applied, and if the A is greater than the yield acceleration, then how the velocity will change and the relative displacement will change. Now, we have I have shown that if the pulse is applied for a duration of del t, and it is a single pulse where starting time is t0 and t0 and the end 1 t0 plus del t, then the velocity will start increasing from t0 point and it will reach at a highest value at t0 plus del t, then it will start reducing again when the pulse is over, and then it will reach a 0 value at t equal to t1. Similarly, the displacement at t0 it was 0, then it will increase this relative displacement as the A or applied acceleration is greater than the yield acceleration. Okay, then this relative movement will come into picture. Now, if and I have already derived that at maximum velocity, what is the value of maximum velocity? That is A minus Ay into del t, and at that point means t equal to t0 plus del t, the relative displacement is half into A minus Ay into del t square. Now, at t0 plus del t, the base acceleration is equal to 0. Okay, this applied base acceleration is drops to 0 at this point. Okay, or I should write that it should be 0, but that means the base acceleration drops to 0. The block continues to move or slide on the plane or decreasing velocity. Which finally reaches to 0 at t equal to t1. So, that decreasing velocity, you can see that means here it is increasing velocity from t0 to t0 plus del t, then is a decreasing velocity from t0 plus del t to t1, and t1 it is 0. Now, what would be the relative acceleration, because that will be not acceleration, because now it is decreasing velocity. So, that acceleration, relative acceleration at this range from t0 plus del t to t1, that will be again ABT minus AY, that is same. Now your ABT is equal to 0 minus A1 AY, so that will be equal to minus AY, and time will be T0 plus del T to T1. Okay, so that will be in this zone. Now here I can write that T1 is the time at which relative velocity is equal to 0. So now you calculate, now we know in this region, in this zone, time zone, what is the relative acceleration. Now I will calculate the relative velocity, that will be equal to the maximum velocity is up to relative velocity at T0 plus del T, that there the maximum velocity is there. Now it will start reducing, so that is plus, now there will be decreasing velocity, so that is starting from T plus del T and it will go to a time, and here it is a relative velocity into dt. So that means here that is basically deceleration, because now it is negative, your acceleration is negative, relative acceleration. So that means up to this point, so this is my maximum velocity, this is the maximum relative velocity, maximum value at this point. So from there is a negative acceleration, though the velocity will start decrease. So now from the maximum one, if I subtract that amount of reduction, then I will get the velocity at that point. Okay, so that is the case. So now here I can write, so this portion is applicable, this is the maximum. So here this is the time is equal to T0 plus del T. This one is in between T0 plus del T to T1, say. I have written any time, later on I will calculate the T1 also. That means this is valid in between T0 plus del T to T1, and this is the maximum. Now there will be subtraction will start. So that means here I can write that this maximum value is how much? Maximum is A minus A1 into del T. So I can put this is A minus AY into del T, that is the maximum relative velocity at T0 plus del T. So that I can write, then plus T0 plus del T to T. Now the relative acceleration is AY into T. Okay. So now if I write that A minus AY into del T, then plus, it will be negative, or I can write plus minus AY. So into, this will be T minus T0 minus del T, up to integration putting the limit, because it will be only T, limit T2 at T0 plus del T to T. So this is the case. Now if I simplify that, it will be AY del T minus AY del T, AY T, then plus AY T0 plus AY del T. So this AY del T will cancel. So it will, if I further simplify that, it will be, or there is a del T here also, it will be capital A del T minus AY, then T minus T0. Okay. So, this is the equation of the, now this equation is valid. You can see that if this equation is mainly valid if I put t equal to, if I put here that my, if your t is equal to T0 plus del t. So, if I put T0 pi del t, it will come back to that maximum velocity. Okay, a minus AY into del t, obviously. So, that means here basically this equation is valid beyond this T0 pi del t condition in this region when the acceleration is, base acceleration is 0. So, now I know that your at t equal to T0, T1, our relative velocity, that will be 0, because this is the condition that this is t equal to T1, relative velocity is 0. So, if I put that this will be 0, where a into del t minus AY, t will be T1 minus T0. Okay. So, now if I simplify, I will get from here the T1 is equal to T0 plus A by AY into del t. AY by A into del t. So, this is the expression of T1. Clear? So, now I know the time where the velocity, relative velocity is 0. Next, I have to calculate at this point what would be the relative displacement. So, now I will calculate the relative displacement. Okay. So, that will be again the displacement at T0 plus del t plus the additional displacement that will occur during that, because block will still to slide, but with a decreasing velocity, but that means there will be further displacement. Here you can see that this is the displacement at T0 plus del t. Then when there is no acceleration, the block will slide with a decreasing velocity. Okay, and then relative acceleration is negative, you can see, but still there is a movement and there will be further deformation, although that rate of deformation is less compared to your T0 to T0 plus del t time region, but still there will be some deformation. So, that means here this is the deformation at T0 plus del t, then I will add the deformation with an decreasing velocity. Okay. So, that is why I will write that this is d relative velocity displacement at t plus del t plus it is T0 plus del t to t, and there will be a relative velocity with time t into t. So, now and at this point, so this is how much? This is half into a minus AY into del t square. This is the value, you can see this is half a minus AY into del t square. So, this is the value, and plus if I do the integration, then I will put T0 plus del t into t. What is the value I will put? I will put this value, a minus capital A del t minus AY t minus T0 into dt. Okay. Now, again if I integrate that, so I will get the integration that half A minus AY into del T square, then plus there will be A capital A into del T into T after integration, and if I put the limit, the integration, that will be T minus T0 minus delta T. Okay. This is basically delta T, and then minus AY, this will be half T square. So, in the T square, if I put the limit, it will be T square minus T0 plus del T whole square. Okay. Then minus, again minus T0 into, if I put the T0 into T, and in the T, if I put the limit, this will be T minus T0 minus del T. So, this is the integration after putting the limit. So, this is the, if I do the integration, I will get this value, and if I simplify this equation, then I will get that relative displacement will be half A minus AY del T square plus A del T, T minus T0 minus del T minus AY half T minus T0 square minus del T square. So, this is the expression. Okay, and it will be valid mostly this region, this region. Okay, so it will be in this region. So, now if I put that, if I want to determine that this relative displacement at T1, that when T is equal to T1, sorry, T equal to T1. When T equal to T1, then I have to put this T1 value. If I put this T1 value, it will be half A minus AY into del T square, then plus A del T into T value is what? T value is this one, because T1 is T0 plus AY del T. Now, your T is equal to T1, because I want to determine the relative displacement and T equal to T1. So, I will put this value T0 plus A by A1 into del T, okay, then minus T0 minus del T. Then similarly, here also half AY, then in the bracket in place of T I will write T0 plus A by AY into del T, then minus T0 whole square, then minus del T whole square. And now, if I simplify this one, so I am not writing those steps, just simplifying that. So, I will get the final value, that is half A minus AY. So, I can remove the bracket here, there is no need to write this bracket. So, half into del T square into A by AY. Okay. So, this is the total displacement, okay, because this is the your you can see there, here you will get this displacement value. So that is my total maximum displacement or total displacement. So this is the relative displacement that will reach this value. So I can write that the total relative displacement that is equal to half capital A minus AY del T square capital A by AY. Now here it is quite obvious, the sliding block model which provide zero permanent slope displacement if your Amax or the maximum acceleration that you are applied in that plane or the plane which is subjected to this Amax acceleration, if it is less than equal to A1 or this AY divided by Amax is greater than equal to 1, so definitely that it will provide zero permanent slope displacement. Okay, and so obviously, so this displacement will start if your Amax is greater than AY. Okay, so now for rectangular pulse, then I can I know that this is my relative displacement or maximum total relative displacement, that is A square, or I can write A square by AY. So that I know that this is half A minus AY del T square into A by AY. Now if I take A outside from this bracket, then I can write that this is half A square by A del T square. This will be 1 minus AY by A. Okay, that I can write. Just I am taking the A outside from this bracket. So now here I can write that this will be V max square divided by 2AY into 1 minus AY by A. What is V max? Now I can write that V max is equal to your acceleration into time del T. That is the your V max, that your amplitude is A. So that means acceleration into time, that will give you the maximum velocity. So here I can write V max is the peak base velocity. I can write that. Okay. Now this pulse is given. Which type of pulse? It is the rectangular type of pulse is given. Okay, it's a rectangular type of pulse is given. Similarly, the closed form solutions are available, or solutions are done for triangular pulse, for sinusoidal pulse. But in case of rectangular or this type of pulse, we can give the base acceleration as the real earthquake acceleration. That also we can give, and we can do the solution. Now that's Newmark found that the permanent displacement produced by different earthquake motions, and then they observe that if the different earthquake motions are being applied as acceleration in place of this rectangular block, because I have done with a simple rectangular pulse, but similarly the real acceleration can be given. So if this analysis can be done for real earthquake motion or for different earthquake motion, and Newmark has done that, and then given a upper bound value of d, that means the maximum value of d, this permanent your displacement. So this is the permanent displacement, and that is the upper bound. And what is that value they have given? They have given V max, or the Newmark has given V max square into 2AY into A max by AY. But this equation is valid if AY by A max is greater than equal to 0.17. Okay. Now, sliding block analysis with actual earthquake motion shows the permanent displacement in centimeter caused by actual motion also. When the Newmark has given the upper bound permanent displacement D max, maximum value, by this analyzing this with the your real or the different earthquake motions, and provided this D max equation. Similarly, if the real earthquake motion is given in this analysis, and then the permanent displacement can also be determined by using this equation. So that equation is log u 0.9 plus log 1 minus AY by A max to 2.53 into AY by A max into minus 1.09. Okay, and similarly the standard deviation of log u, that is equal to 0.3. So in addition to that, based on this Newmark sliding block analysis, other equations, different equation for to determine the or for determining that permanent displacement is given. So I have given you these two equations. One is that with this, which is provided by Newmark, that upper bound displacement permanent displacement equation, and this is the another equation where thus this analysis is being done for real earthquake, and we got this equation where we will get the permanent displacement. So this is also the permanent displacement. Okay, but again this equation is valid if AOI by A max is greater than 0.1 was less than 0.9, and the surface wave magnitude is in between 7.3 to 6.6. So remember that this equation is valid for the surface wave magnitude 7.3 to 6.3, and we will get this permanent displacement value. Now, let me solve one small example problem, that for a site 1, say here I have a max value. You can see this is my max, maximum acceleration here. This will be around from the site 1. If this is your acceleration and time history, max value is around 0.45 g, and velocity, you can see the velocity for this for site this earthquake, and this is around 38. So that means the maximum velocity or peak velocity is 38 centimeter per second. So we have velocity is 38 centimeter per second, and the max is 0.45 g. And we have already solved one problem in my previous lecture, where under seismic condition or static by seismic condition, we got a factor of safety which is equal to 1. So previous lecture also I have discussed that as that is the factor of safety when is equal to 1. So the corresponding acceleration is the yield acceleration. So there also the corresponding acceleration was applied as 0.15 g. So now if I consider the same problem and I want to determine what would be the permanent deformation if 1.45 g acceleration is been applied, because the yield acceleration is 0.15 g in that problem that I solved, okay, on my slope stability analysis problem where I applied the pseudostatic approach. So there we got a yield acceleration of 0.15 g. Now for the same problem, if I apply a acceleration of 0.45 g, what would be the maximum displacement by using this Newmark expression? So here I can see that A max, if A max is equal to 0.45 g, velocity or maximum peak velocity is 38 centimeter per second, and yield acceleration is 0.15 g. The same example problem I am taking, and I want to determine the maximum permanent deflection or displacement. So this is given V max square divided by 2 AY, A max by AY. So it will be 38 square divided by 2 into 0.15 into, this is A max is 0.45 g and this is 0.15 g. Here also it is g. So these two g will cancel, but there will be another g. So there I have to put value. So 38 square divided by 2 into 0.15 into 981 into 0.45 divided by 0.15. So here the 2g will cancel, but here I have to put the value of g is 981 centimeter per second square. Okay. So that value we can put here. So here also it is centimeter square. Here it is centimeter per second square. The centimeter per second, that means whole square. So ultimately the unit will be centimeter. So here, from here, if I put this value, it will be 14.72 centimeter. Okay. So similarly, you can use the other expressions also if your condition, these conditions are being satisfied. Here, if it is surface wave magnitude is in between 7.3 to 6.6, then and this A max, AY by A max is in between 0.1 to 0.9, then you can use the other expression also. I have used this expression, I will get the permanent displacement D max, which is the proposed by Newmark, that is value is 14.72 centimeter. Okay. So this is the end of this seismic slope stability part, and in the next class I will start the seismic retaining wall design. Okay, so and I will use the pseudostatic, pseudodynamic, and I will consider do it for our normal retaining wall and then the reinforced retaining wall also. Thank you.